Okay, so the very last thing that we're going to do to put all the pieces of our organic puzzle together is talk about organic pathways and how we go about planning out making more complex molecules from the different reactions that we have. Essentially, and we should all have a map of our synthetic routes or the reactions we need to know for each of the compounds that we've studied so far, is that this forms a map of how we might get from one substance to another. Okay, so we talked about how we can form from an alkane, we can form halogenoalkanes, and from there we can form alcohols, or we can form esters, carboxylic acids through to aldehydes and alcohols, through either going from the alcohol out through oxidation or coming back to the alcohol through reduction. So we have a huge number of reactions that we can now use to build up a pathway to get from one molecule, maybe a smaller molecule, all the way through to a much more complex molecule using multiple stages. When we do this, we call it a synthetic route or a synthetic pathway. This provides us a series of discrete steps where we are producing compounds along the way towards getting to the final product. We use this for the development of many organic compounds, drugs, dyes, clothing, fibers for polymers, things like that, as well as construction materials. So anytime a chemist wants to start planning out, oh, I want to make this molecule, it might be a natural product, it might be something that they believe will be effective against a particular disease, they need to work out exactly how they're going to make it from smaller molecular components that can be purchased. Typically, we begin with readily available starting materials and convert these using a series of steps into more functional compounds that we can manipulate the functional groups to get what we're after. The way we do this is we use what we call a retrosynthetic analysis. This is where we work backwards from the desired target molecule and then look at the functional groups that can be broken down into smaller fragments and then work out how to make each one of those fragments until we can use something that we can start the synthesis. This will usually be something like a simple alkene or maybe an alkane that we can start our synthesis from. So essentially we're working backwards. We know what we want to make, and then we go back and break it down into the steps that we need to get there until we have the simplest starting materials and can start our synthesis. Using this wide two-line arrow like this is a retrosynthetic arrow. So that's telling us that it can be made from rather than we are making something to get to that. It's sort of like indicating the reverse process. We use this in pharmaceutical and other industries a lot, and quite often this is done using computer programming and various other bits to help us pull apart molecules to work out what we can start with. So let's have a quick look at an example. This one is asking us how to make propylpropanoate from a single carboxylic acid. So we have to give the equations and conditions for all reactions and state the type of reaction occurring at the functional group at each step. So we're going to start with propylpropanoate, and this is going to be a very simple example. So we would draw it out, 1, 2, propyl into my alcohol, out to my carboxylic acid, 2, 3, remembering 3 carbons, so 1, 2, 3. Fill in all our hydrogens. Okay, so if we're going to do a retrosynthetic analysis, we're going to use our retrosynthetic arrow. This is going to say we're going to cleave this bond here, and we will therefore be able to make it from 1, 2, 3. So we're going to need this carboxylic acid. Okay, and we're going to, it said 1 carboxylic acid. So the other thing that we need is, of course, going to be propanol. So we need to suggest a way that we can get from propanol or from the acid to propanol. And that will be in the reactions that we've just looked at, which would be a reduction, because I want to go from a carboxylic acid to the alcohol. And if you remember, our reduction is going to be lithium aluminium hydride in dry ether, and heat will be the reduction process for that. So now we can do our retrosynthetic analysis. I'll do it on this slide. So we're going to start with our propanoic acid. Ooh, got one too many. Start with our propanoic acid. We're going to reduce part of that using lithium aluminium hydride and dry ether and heat to produce propanol. Then we would take another portion of this, reacting it with that in order to produce in the presence of H2SO4 as a catalyst to produce our ester. So this is using the different reactions that we have up our sleeve to put together a pathway on how we could make this molecule, our propylpropanoate, just from the one carboxylic acid. Now I want you to think about, can you write a pathway for this same molecule where we're going to start, we have the acid, but perhaps we want to start from a more simple compound. So we could start from the alcohol. So we could start from our alcohol. Whoops, should have our alcohol here. We can start from our alcohol and go through, or better still, can you suggest a pathway starting from propane? How we would manufacture and get through to propanoate. Of course, this is going to be a much longer synthetic pathway. And that's it. That is officially the end of HL Organic. Of course, we will practice a number of these pathways in class in order to review our organic chemistry and get ready for our test. I'll see you in class.